Hello and welcome to Earth Science Lecture 24, Climate Change, Part 3. Increased atmospheric carbon dioxide is of concern because this strengthens the greenhouse effect and raises Earth's average surface temperature. This figure also shows how this average temperature has varied since the year 1000. Like the CO2 data, the temperature data from past centuries comes from analyzing trapped air bubbles. Scientists measure the relative amounts of two different types of atmospheric oxygen called oxygen-16 and oxygen-18 in a bubble. The ratio of these is a sensitive measure of the temperature at the time the air was trapped inside the bubble. The recent dramatic increase in the atmospheric concentrations of carbon dioxide has produced an equally dramatic increase in the average surface temperatures. This temperature increase is called global warming. As we will soon explore, other explanations for global warming have been proposed, such as volcanism and changes in the sun's brightness, but only greenhouse gases produced by human activity can explain the steep temperature increase shown. So I am going to pull up a chart here to take a look at. Let's see. Okay, so here is a really interesting graphic. So I'm going to let this play out a few times. On the left, I'll pause it once it resets here. So on the left, we have yearly CO2 emissions. So this is how much we're outputting. In the middle, we have monthly CO2 concentration. So that's how much is stored in the atmosphere. And on the right, we have temperature change. So let's go ahead and let this play out. So over time, since roughly the Industrial Revolution, we have been using more and more more and more fossil fuels, so we've been releasing more carbon dioxide into the atmosphere. So that's what this chart's showing. So, of course, naturally, we see more stuck in our atmosphere. And because CO2 is a greenhouse gas, it's like adding blankets to the atmosphere, so we see our temperatures rise as well. So we'll let this play out one more time, and I'll also link this in the YouTube description so that you have this to look at on your own time as well, if you'd like to. So focus mostly on the temperature increase and the CO2 concentrations, and notice how they go hand in hand. All right. So let's return. Okay. So here is that global temperature change chart shown up close. So we're going to look at this once or twice here. So this shows, again, monthly temperatures, so January through December, and it shows the temperature increasing outward from the center throughout the years. There's two red lines on here, by the way, the 1.5 and 2. 1.5 and 2 degrees Celsius, our temperature is set by an international pact on climate change. 1.5 is basically our goal, so we don't want to go past that. 2 is like our ultimate goal, and beyond that it starts to become troublesome. So here's just another way to present that data. So this is our temperature increases since, again, roughly the Industrial Revolution in the 1800s. So notice that there is a general trend in which temperatures are increasing over time. The main reason I threw this one in addition to everything else, is that it shows El Niño years. So El Niño is a short period of time where temperatures rise in certain parts of the world, and so we tend to get a slight enhancement of our temperatures over time. And so that's why, for example, from 2014 to 16, we had very strong record warm years. Well, it's because there was a strong El Niño in that year. And so 2017, I believe, was the fourth warmest, or maybe it was 2018, but either way, it drops back down a little bit for a while as El Niño weakens again. So here's another way to analyze all of this. 2018 was the fourth hottest year since modern record keeping began. NASA and the National Oceanic and Atmospheric Administration worked together to track temperatures around the world and study how they change from year to year. For decades, the overall global temperature has been increasing, and as you notice from this graphic, it's increasing the most in the Arctic, the upper latitudes of the Northern Hemisphere. So to slow that graphic down, here's just a still image of those temperatures, the average from 2014 to 2018. And you'll notice again that most of the warming, or the more severe warming, is occurring over the northern latitudes up in the Arctic. So we're going to take a look at another chart here. So we can get this pulled up. So the whole idea is that, yes, the climate has changed in the past. We know this, of course. There have been warmer periods and cooler periods. but what's alarming is the rate at which it's occurring. And so this chart is really useful in displaying that information. So what this shows, and there's a lot of reading involved in this, which I won't go through, so I'm going to link this in the YouTube description as well for you to read at your own time if you'd like. This shows temperatures, the average being right in the center. Anything colder than average today is to the left, anything warmer is to the right. And we're starting at 20,000 BCE, so very long ago. So of course it started much colder in this time, 4.3 degrees colder than it is today. So let's take a look at how the temperature changed over time as I scroll. And again, you're not expected to be able to read this as I do this. So over long periods of time, so here we've gone through almost 10,000 years already, we've seen the temperature increase a bit, but it's still below today's average. So we see it alternating back and forth, back and forth. By the time we reach our maybe 10 to 7,500 years BCE, we are a little bit warmer than today's average, so it has been warmer in the past. So just going to keep going here. So we're still warmer, still warmer. My dog is sneezing in the background. Sorry if you heard that. So by the year 0, or 1 CE, or 1 CE, or 1 BCE, basically the same thing, we're back to modern day temperatures. And then take a look at what happens here. Suddenly the temperatures skyrocket. So it's the rate at which the temperatures are increasing that is the most alarming, not the fact that it's just slightly warmer than it was before. And then this also includes 3 scenarios in which the temperature will continue to increase on. The current path just highlights what would happen if we don't change anything, which would be the worst scenario. At best, though, we should be able to stop it a little bit further if we can kind of remove all of our emissions entirely, but we'll see how that goes. Okay, so then we can move to what's really warming the world. So we've talked already in this lecture or series of lectures that we know it is human activity, but people still have the questions of, well, what about the sun, or what about volcanic activity? What does that have to do with it? So let's take a look. So I am going to show this really awesome interactive chart from Bloomberg that shows what's really warming the world. And so I'll just read along with this as we go. What's really warming the world? Skeptics of man-made climate change offer various natural causes to explain why the Earth has warmed by 1.4 degrees Fahrenheit since 1880. But can these account for the planet's rising temperature? So let's scroll down and find out. So here's the chart of our observed temperature increase over the years. So let's start with the Earth's orbit. The Earth wobbles on its axis, and its tilt and orbital change over many thousands of years, so pushing the climate into and out of ice ages. Yet the influence of orbital changes on the planet's temperature over 125 years has been negligible, shown by this blue color down here. Well, is it the sun? The sun's temperature varies over decades and centuries. These changes have little effect on the Earth's overall climate so far. So the sun doesn't seem to have any effect either. What about volcanoes? The data suggests no. The human industry emits about 100 times more carbon dioxide than volcanic activity, and eruptions release sulfate chemicals that can actually cool the atmosphere for a year or two. So even though the volcanic activity has varied on our graph more than the others, it still seems to not match up with our observed change. So let's combine all these natural factors. Is it all 3 of them combined? Well, if it were, then the response to natural factors should match the observed temperature. Adding these natural factors together does not add up. So if it's not nature, could it be deforestation? Humans have cut, plowed, and paved more than half of Earth's land surface. Dark forests are yielding to lighter patches, which reflect more sunlight and have a slight cooling effect. So deforestation is not on its own causing our increased temperature. Is it ozone pollution? Natural ozone high in the atmosphere blocks harmful sunlight and cools things slightly. But closer to the Earth, ozone is created by pollution and traps heat, making the climate a little bit more warm. But the overall effect is not much. Notice that it does not match our graph even yet still. What about aerosols? Well, some pollutants cool the atmosphere, like sulfate aerosols from coal burning. These aerosols offset some of the warming. So here we actually see the opposite effect. Well, It really is greenhouse gases. Atmospheric CO2 levels are 40% higher than they were in 1750. This green line shows the influence of greenhouse gas emissions. It's no contest. So let's combine our human influences. Greenhouse gases warm the atmosphere, aerosols cool it a bit, ozone and land use changes add and subtract a little bit. Together, they match our observed temperature change, particularly since 1950. So let's compare and contrast. Let's put everything together. Both natural and human causes of climate change alongside one another makes the dominant role of the greenhouse gases even more plainly visible. So the only real question is, what are we going to do about it? So this brings us then back to my lecture. Let's see. This brings us to our third important takeaway of 3. Climate models that ignore human activity fail to match the observed rise in global temperatures. In contrast, climate models that include the enhanced greenhouse effect from human productions of greenhouse gases match the observed temperature trends quite well. Comparisons between observations and models therefore clearly indicate that global warming results from human activity. So now we can finally discuss the last section of our material for this lecture, the consequences of climate change. So how will our planet and we be impacted? Note that there's a lot to talk about here. We're just going to focus in on a few different things and just let the rest be something you can research if need be. So the same models that convince scientists of the reality of human-induced global warming tell us that if current trends in the greenhouse gas concentrations continue, that is, if we do nothing to slow our emissions of CO2, the warming trend will continue to accelerate, as you can see on the right. By the end of this century, models predict that the global average temperature would be 6 to 10 degrees higher than it is now, giving our children and grandchildren the warmest climate that any generation has ever experienced. So watch this graph again. It's similar to the one we've seen in the past, so it's showing temperatures increasing, but this one goes beyond and predicts the future temperatures if we don't change our emissions. And it's quite terrifying, as temperatures can rise from 5 to 10 degrees higher than they are already, up until 2100, as you can see in this graph. Climate is a very complex interactive physical system. Thus, when any component of the climate system is altered, scientists must consider many possible responses, some of which amplify the initial effect and some of which counterbalance it. These possible responses are called climate feedback systems. One important mechanism is that warmer surface temperatures increase the evaporation rates on the surface. This in turn increases atmosphere's ability to store water vapor. Remember that water vapor is a powerful absorber of radiation energy from the Earth. In other words, it's another greenhouse gas. Therefore, an increase in atmospheric water vapor tends to reinforce the temperature increase caused by carbon dioxide emissions. Recall that the future temperature increase at high latitudes may be 2 to 3 times greater than the global average. In other words, it's going to warm more in the Arctic. This projection is based in part on the likelihood that the area covered by sea ice will decrease as surface temperatures rise. Because ice reflects a much larger percentage of incoming solar radiation than does open water, its melting results in a substantial increase in the solar energy absorbed at the surface. This in turn magnifies the temperature increase created by higher levels of greenhouse gases. The climate feedback mechanisms just described magnify the temperature rise caused by the buildup of carbon dioxide. Because these effects reinforce the initial change, they are called positive feedback mechanisms. Conversely, negative feedback mechanisms produce results that are just the opposite of the initial change and tend to offset it. What consequences can be expected as the carbon dioxide content of the atmosphere reaches a level that is twice what it was in the early 20th century? Well, because the climate system is complex, predicting the occurrence of specific events in particular places is speculative at best. It is not yet possible to pinpoint such changes. Nevertheless, there are plausible scenarios for larger scales of space and time. As noted, the magnitude of the temperature increase will not be the same everywhere. The temperature rise will probably be smallest in the tropics and increase toward the poles. As for precipitation, the models indicate that some regions will experience significantly more precipitation and runoff. However, others will experience a decrease in runoff due to reduced precipitation or greater evaporation caused by higher temperature. This table that you see lists possible effects of global warming based on the IPCC's projections for the late 21st century, ranked in decreasing order of certainty. Probabilities are based on the quality, volume, and consistency of the evidence, and the extent of agreement among scientists. The risk associated with each of the projections in the table is a combination of the probability of occurrence and the severity of damage, if it were to occur, of course. This means that even projections labeled unlikely should not be ignored, because if any of those events were to happen, the consequences would be extremely serious. So I'm not going to read through all these, I'll leave them to you, but we will focus on several of these in the next few slides. A significant impact of human-induced global warming is a rise in sea level. As this occurs, coastal cities, wetlands, and low-lying areas will be threatened with more frequent flooding, increased shoreline erosion, and saltwater encroachment into coastal rivers and aquifers. How is a warmer atmosphere related to a rise in sea level? Well, one significant factor is thermal expansion. Higher air temperatures warm the adjacent upper layers of the ocean, which in turn causes the water to expand and the sea levels to rise. This effect alone is likely to cause sea levels to rise another 30 centimeters during this century. A second factor contributing to global sea level rise is melting glaciers. With few exceptions, glaciers around the world have been retreating at unprecedented rates over the past century, some of which have disappeared altogether. A satellite study spanning 20 years showed that the mass of the Greenland and Antarctic ice sheets dropped by an average of 475 gigatons per year, or 475 billion metric tons. That is enough water to raise the sea levels by 1.5 millimeters or 0.05 inches every year. The loss of ice was not steady, but was occurring at an accelerating rate during the study period. So, as you can see here, we can see this acceleration. So this shows sea level anomaly, which is showing the rise over the years. And it's been rising the entire time, but not only that, it's been rising at an increasing rate. So 0.8 millimeters per year, then 1.9, then 3.1. So not only is sea level rising, but it's rising faster and faster. So this graphic here, this animation, shows sea level rise. Since the 1880s, sea levels have risen by an average of 8 centimeters, 8 inches throughout the entire globe. So that's not the whole point, though. The whole point isn't to look at the past. The point of this part of the lecture is to look forward. So what about future changes in sea level? Well, scientists realize that even modest rises in sea level along a gently sloping shoreline, such as the Atlantic and Gulf coasts of the United States, will lead to significant erosion and severe permanent inland flooding. If this happens, many beaches and wetlands will disappear and coastal civilizations will be severely disrupted. If these trends continue, sea level could rise as much as several meters, enough to flood most of Florida by the end of the century. Low-lying and densely populated places such as Bangladesh and the small island nation of the Maldives are especially vulnerable. The average elevation, for example, of the Maldives is just 5 feet, and its height at the highest point is just 8 feet above sea level. Because rising sea level is a gradual phenomenon, coastal residents may overlook it as an important contributor to shoreline flooding and erosion problems. Rather, the blame may be assigned to other forces, especially storm activity. Although a given storm may be the immediate cause, the magnitude of its destruction may result from the relatively small sea level rise that allowed the storm's power to cross such a great land area. As this figure on the bottom right indicates, the estimates of future sea level rise are uncertain. The 4 scenarios depicted on the graph represent estimates based on different degrees of ocean warming and ice sheet loss, and range anywhere from 8 inches to 6.6 feet. So it is most likely that we'll end up along one of these intermediate paths, probably the orange one. The lowest scenarios aren't realistic because it follows ocean level rises from the past, not what's actually happening today. The effects of global warming are most pronounced in the high latitudes of the northern hemisphere, in other words, in the Arctic. As this moving graphic in the middle shows, this shows how temperatures are rising by latitude. So we see the temperature change up at the top. The further to the right, the warmer it is, and it's showing you based on latitude. So down in the middle, near the tropics, it's warming a little bit, but at the Arctic levels, it's rising a lot. For more than 30 years, the extent and thickness of sea ice has been rapidly declining. In addition, permafrost temperatures have been rapidly rising, and the area affected by permafrost has been decreasing. Meanwhile, alpine glaciers and the Greenland ice sheet have been shrinking. Another sign that the Arctic is rapidly warming is related to plant growth. A 2013 study showed that the vegetation growth at northern latitudes now resembles that which is characterized for areas 4 to 6 degrees latitude further south. So that's 250 to 430 miles further south. We're seeing plant life, as it should be, that far down. So as one researcher characterized this finding, they said it's like Winnipeg, Manitoba moved to Minneapolis, St. Paul in just 30 years. So this is an issue. But one of the biggest issues and one of the most telling evidence of global warming is the loss of sea ice in the Arctic. And this is indeed occurring. Not only is the area covered by sea ice declining, but the remaining sea ice has become thinner. As you can see in this graphic, so you can see the ice declining from time to time. The white is the thick ice, gray is thin ice. And not only is its area becoming smaller, but it's becoming thinner, which of course makes it more vulnerable then to future melting. So models that best match historical trends project that Arctic waters could be virtually ice-free in the late summer by the 2030s. As we noted earlier, a reduction in sea ice represents a positive feedback mechanism that reinforces global warming. The effects of climate change aren't observed only in the Arctic. Just as an example, in July of 2017, an iceberg the size of Delaware broke off the Antarctic Larsen Sea ice shelf and began to drift across the choppy waters of the ocean. Although this is a natural process, scientists fear that global warming will accelerate the rate at which other ice shelves, including those around Canada's islands, will break up. Because ice shelves are already floating in the ocean, they themselves do not contribute directly to sea level rise. However, glaciers constantly push up against them, and so if these ice shelves are gone, the glaciers are now free to slowly move into the oceans, which can cause significant rises in sea level. So this graphic on the bottom just shows the volume of sea ice in the Arctic, and it goes from blue to red from past to present, and it shows seasonal variations, of course. So when it's warmer, you have less ice, and when it's colder, you have more ice. And we see it's very obviously declining from past to present. So this animation here is a conceptual one showing how polar ice is reflected from the sun. As this ice begins to melt, less sunlight gets reflected into space. It is instead absorbed into the oceans and land, which raises the overall temperature and fuels even further warming. And so that's what this is just showing in this graphic. Okay. Well, there's other ways to analyze this. Permafrost is permanently frozen ground that occurs in large portions of the high latitudes of the northern hemisphere. So as you can see from this top-down view of the North Pole, it shows where permafrost exists. Evidence indicates that the extent of permafrost in the northern hemisphere has decreased over the past decade, as would be expected under long-term warming conditions. Studies in Alaska show that thawing is occurring in the interior and southern parts of the state, where permafrost temperatures are near their thawing point. As Arctic temperatures continue to rise, some models project that near-surface permafrost may be lost entirely from large portions of Alaska and surrounding areas by the end of the century. Thawing permafrost represents a potentially significant positive feedback mechanism that may reinforce global warming. When vegetation dies in the Arctic, cold temperatures inhibit its decomposition. As a consequence, over thousands of years, a great deal of organic matter has become stored in the permafrost. But when the permafrost thaws, organic matter that may have been frozen for millennia come out of their cold storage and begin to decompose. The result is the release of carbon dioxide and methane, both greenhouse gases that contribute to global warming. Thus, like decreasing sea ice, thawing permafrost is a positive feedback mechanism that will make global warming worse. The human-induced increase in the amount of carbon dioxide in the atmosphere also has some serious implications for ocean chemistry and marine life. Nearly half of the human-generated carbon dioxide ends up dissolved in the oceans. When carbon dioxide from the atmosphere dissolves in seawater, it forms carbonic acid, H2CO3. This lowers the ocean's pH and changes the balance of certain chemicals found naturally in seawater. In fact, the oceans have already absorbed enough carbon dioxide for surface waters to have experienced a decrease in pH of 0.1 since pre-industrial times, which means that the seawater is becoming more acidic. Moreover, if the current trends continue in our CO2 emissions, by the year 2100, the ocean will have experienced a pH decrease of at least 0.3, which represents a change in ocean chemistry that has not occurred for at least millions of years. This shift toward acidity and the resulting changes in ocean chemistry make it far more difficult for certain marine organisms to build hard parts or shells out of calcium carbonate. The decline in pH thus threatens a variety of calcite-secreting organisms as diverse as microbes and corals. This concerns many marine scientists because the potential consequences for other sea life because of the potential consequences for other sea life that depend on the health and availability of these organisms. So it could have a lasting effect on many marine organisms. The oceans are mostly composed of warm, salty water near the surface over cold, less salty water in the ocean depths. These two regions do not mix except in certain areas. Ocean currents, that is, the movement of the ocean, say at the surface, are driven mostly by the wind. In certain areas near the poles, we see colder surface water also get saltier due to evaporation or sea ice formation. In this region, the surface water becomes dense enough to sink to the ocean depths, as you're seeing right now. This pumping of surface water into the deep ocean forces deep water to move horizontally until it can find an area in the world where it can rise back to the surface and close the loop. This usually occurs along the equatorial oceans, mostly in the Pacific and Indian Oceans. This very large, slow current is called the thermohaline, which is called that because it's caused by temperature and salinity variations. Salinity is another term for it is haline. In a far-reaching study, the scientists combined more than 2 million observations of ocean salinity with more than 370 simulations conducted with climate models running on supercomputers to mimic atmospheric and oceanic processes, including precipitation, evaporation, and the resultant changes to ocean salinity. The findings suggest that since 1950, ongoing climate change has caused the entire global water cycle to intensify. Intensification is characterized by greater rainfall over some ocean areas, which is locally reducing the salinity, and by increased evaporation in other parts of the sea, making those areas saltier. In short, ocean salinity is changing approximately twice as much as had been predicted by the current generation of climate models. So this animation we're watching shows one of the major regions where this pumping occurs, the North Atlantic Ocean around Greenland, Iceland, and the North Sea. The surface ocean current brings new water to this region from the South Atlantic via the Gulf Stream, and the water returns to the South Atlantic via the North Atlantic deep water current that you see in blue. The continual influx of warm water into the North Atlantic polar oceans keeps the regions around Iceland and Greenland mostly free of sea ice year-round. Okay, so at this point, please pause this video and take a look at the ocean currents video linked in the YouTube description or at the following link. Well, these changes in precipitation patterns don't just matter over water. It matters over land, especially because that's, well, where pretty much all of us live. Before we get into the context too much, I want to just highlight what these animations are showing in the meantime. The top visualization shows model projections of the precipitation anomalies from the year 2000 to 2100 as a percentage difference between the 30-year average. So what this is basically showing is that we tend to see more precipitation occurring in the northern latitudes and less down south. So it's basically saying more precipitation, less precipitation. And of course, as a result of that, we see a change in soil moisture. The bottom visualization shows soil moisture at the surface down to 30 centimeters from 1950 to 2100, based on some models that we have. And what we see is that we see lots of drier soil in brown and more moist soil in blue. And you can see how well it correlates with the top animation. So anyway, let's dig into this. Higher temperatures lead to an increased rate of evaporation, including more loss of moisture through plant leaves. Even in areas where precipitation does not decrease, these increases in evaporation and loss of water from plants will lead to rapid drying soils. Droughts in the southwest and central plains of the United States in the second half of the 21st century could be drier and longer than anything humans have seen in those regions in the last 1,000 years, according to a new NASA study published in 2015. The research found continued increases in human-produced greenhouse gas emissions drives up the risk of severe droughts in these regions. Natural droughts like the 1930s Dust Bowl and the current drought in the Southwest have historically lasted maybe a decade or less, said Ben Cook, climate scientist of NASA's Goddard Institute for Space Studies and the Lamont Doherty Earth Observatory at Columbia University in New York, and lead author of this study. What these results are saying is we're going to get a drought similar to those events, but it's probably going to last at least 30 to 35 years. According to Cook, the current likelihood of a megadrought, that is a drought lasting more than 3 decades, is 12%. If greenhouse gas emissions continue to increase along their current trajectories, however, through the 21st century, there is an 80% likelihood of a decades-long megadrought in the southwest and central plains by the year 2050 to 2090. So the scientists analyzed a drought severity index and 2 moisture soil datasets from 17 climate models that were run on both emission scenarios. And so what we're seeing here in these graphics, again, is just the fact that we're probably going to see more severe and longer droughts in the southwest and central plains. Well, that doesn't just mean droughts. The increased evaporation rate also means that the amount of water vapor in the atmosphere has increased. Furthermore, warmer air can contain more water vapor than cooler air. This extra moisture is available for storm systems, resulting in heavier rainfalls. Ironically, this also means that global warming could lead to more severe winter blizzards. Heavy downpours are increasing nationally, especially over the last 3 to 5 decades. The heaviest rainfall events have become heavier and more frequent, and the amount of rain falling on the heaviest days has also increased. Since 1991, the amount of rain falling in very heavy precipitation events has been significantly above average. This increase has been the greatest in the Northeast, Midwest, and Upper Great Plains, more than 30% above the average from 1901 to 1960. There has also been an increase in flooding events in the Midwest, Northeast, and Upper Great Plains, where the largest increase in heavy rain amounts have occurred. Flooding may further intensify in many U.S. regions, even in areas where total precipitation is projected to decline. A flood is defined as any high flow, overflow, or inundation by water that causes or threatens damage. Floods are caused or amplified not only by weather but also by human-related factors. Major weather factors include heavy or prolonged precipitation, snow melt, thunderstorms, storm surges from hurricanes, ice debris and jams, and so on. But the human factors matter too, including structural failures of dams and levees, altered drainage systems, and land cover alterations such as pavement. The risk for future floods is significant, given expanded development in coastal areas and floodplains, unabated urbanization, land use changes, and human-induced climate change. And so this graphic is just showing the percent change in flooding magnitude. So flooding is getting worse in the plains in northeast, and droughts are getting worse in the southwest. So things are becoming more extreme. And what better time to talk about this, unfortunately, than right now? I'm recording this in the spring of 2019, and right now we're seeing the worst flooding ever in Nebraska and Iowa right now. I mean, most of the state is under some amount of water, and it's horrible. And so we're seeing these extremes becoming more common. So with that, we'll kind of conclude this discussion. I could go on forever and talk about all these different things that are being affected, but of course, we don't want to take this on forever. So let's go ahead and have one slide to summarize everything. How do we know that humans are causing the Earth to warm and the climate to change? First off, simple chemistry. Burning carbon-based fuels releases carbon dioxide into the atmosphere. 2, basic accounting. We keep track of and add up how much we burn, and therefore we can calculate how much CO2 and other pollutants we emit. Number 3, measuring in the atmosphere. Measuring CO2 in the atmosphere in remote locations shows that the increasing emissions is indeed increasing atmospheric concentrations. CO2 trapped in ice shows that levels today are much higher than over the past 800,000 years at least. Number 4, chemical analysis. Chemical analysis of the carbon dioxide that we find in the atmosphere reveals that the excess is from burning ancient plants that have been buried for millions of years. In other words, from burning fossil fuels. Number 5, basic physics. We learned about the greenhouse effect. So certain gases, such as carbon dioxide, absorb heat emitted by the Earth and prevent it from leaving into space. So this explains why, of course, a greenhouse is hot, why the Earth isn't frozen, and for example, why Venus is hotter than Mercury even though it's further away from the sun. Number 6, monitoring climate conditions. Independent temperature records show that the Earth is warming, and that this warming trend is correlated with the rise in atmospheric CO2 concentrations from human activities. And we can, number 7, rule out natural factors. Many factors can influence climate conditions, but monitoring and examining natural factors show that they have not played a major role in the warming that we've seen in the 20th century and 21st century. Number 8, we can employ computer models. Computer models are tools that scientists use as a virtual laboratory because we can't experiment with the Earth. Only the inclusion of human activities in climate models can reproduce the observed warming that we've seen. And of course, number 9, we've probably all heard of this before, but there's consensus among scientists. Analyzing the above evidence for themselves, 97% of the 12,000 climate scientists from 74 countries that published in scientific literature between 1994 and 2011 agree that humans are the main cause of climate change. And with that, we will end this discussion. I really hope you've learned something. This topic means a lot to me personally. And I mean, as always, if you ever have questions or concerns or comments or anything to add or take away, let me know. I'd be happy to listen. So as always, thanks for watching and have a great day.